sea level rise. This is one of the areas where there's been most work done for adapting to sea level rise, in part because it's so easy to visualize for the decision makers. They can imagine what's going to happen. And so it's very important to put this whole work in perspective and to do a very good job. So let's start at the beginning. What happened to the sea level at the end of the last ice age? 20,000 years ago, there were 3 miles of ice over New York City. And as that all melted between 20 and about 8 to 10,000 years ago, the sea level rose by about 120 meters. Okay, 120 meters. And then you can see at the last 8 or 10,000 years, the sea level has been relatively constant on this scale of resolution. If you look a bit more closely, there was a recent paper that was published about sea level off the coast of North Carolina that tells you how sea level changed in the last 2,000 years. And what you see from this plot is following the medieval warm period, the temperature profile is at the bottom. The sea level rose, and then it went down during the Little Ice Age, and then you see a rather rapid increase after from about the 19th century to the present. Now, sea level rise has accelerated again in the last 20 years. And if you look at this plot, what you find is a change in the way we are actually estimating sea level rise from tide gauges, distributed tide gauges around the world, which have their own problems with land subsidence and changing of instrumentation. And the final two now, where we use satellite altimetry to measure the altitude of the ocean to about a centimeter accuracy. And this has been going on for about the last 20 years. These measurements are absolute, since the satellites are located relative to the center of gravity of the Earth. And they show about a 3 millimeter per year sea level rise, 30 centimeters a century approximately. So, this is an acceleration, and clearly it's, from the last plot, the fastest that we've had in the last 2,000 years. So now this gets us then to the question, we've now seen what happened in the past, what can happen, and now we get to the question of the projection of the global mean sea level, something that we've discussed in the other lectures as well. And for adaptation purposes, I'm going to emphasize it's not enough just to say that we expect it to rise in the future and to give a range. The key issue for the decision maker is, when are the impacts going to affect them? How much time do they have to make a decision? This then puts a very great burden on the scientific community to estimate better and faster when sea level may occur. As we've said earlier, IPCC 2007 made a serious error in that they underestimated the sea level rise that we would expect to get in the future, because they used only the warming of the oceans and the change in salinity to estimate how much sea level rise would occur. And that was because at that time we didn't know the contributions of the mountains and the ice caps as well as we do now, and they were as a conservative and didn't want to talk about anything for which there was controversy in the scientific community. Now, I was at the meeting in 2007 at the Royal Society about a week or two after the report was released. And I've got to say that as soon as this result came out, there was an uproar in the audience, and everybody knew that they had made a serious mistake because they had not included the ice and snow contribution to the sea level rise. And this was pointed out almost immediately in a famous article by Stefan Rahmstorf, which is cited there. Now I think we can say the second Arctic climate assessment now says that ice, snow, and water melt now contribute about 40 to 50% of the observed sea level rise, and the melt rate doubled in the last decade. As a result of things like these more pessimistic projections, California and the UK, both of whom have done assessments, have increased their expectations for sea level rise in 2100 to 1.4 meters and 1.9 meters. These, I suspect, they think are outer bounds of what can occur, but clearly what you should prepare for. On the other hand, it is also possible that if we work hard on the short-lived climate pollutants, we might be able to reduce the 2100 sea level rise estimates by about 20 to 40% in a new paper that was published by Hugh et al. In Ramanathan's group here just about a month ago. So these projections depend dramatically on what the ice and snow and water are doing. The steric effect we think we understand better. So here are some of the results again. Arctic annual mass loss, Antarctic increased by 75%. Now what you see is that the whole Antarctic ice sheet isn't melting, but there are areas where it is. And there's so much water in those areas that it's making a significant contribution to the observations, and you're seeing an acceleration. The Greenland mass loss rate doubled, okay? So that together, they're adding 13 centimeters a century to the thermal expansion. Okay? And in addition, the second Arctic assessment says the glaciers and mountain ice caps are adding another 4 centimeters, so 17 of the 30 centimeters per century now, in the present time, now seem to be coming from the melting snows. How long that lasts depends on how much fresh water there is in those reservoirs.
Sorry, can I just
Yeah.
one thing? I think it's just a syntax problem. Can you just go back for a second?
Yeah.
When you say Greenland and Antarctica adding 13 centimeters to thermal expansion, you mean above and beyond?
Yeah, above and beyond.
Got it, okay, because
Yeah.
it's not contributing to thermal expansion.
No.
But has anybody looked at, it's probably a second order effect, but I mean, if you have enough fresh water entering the ocean, you decrease the salinity of the ocean, that actually can affect the volume changes.
I worried about the same question. Yeah.
Okay.
It
So
makes
remember not knowing
it makes the seawater denser,
Right.
and that could very well change circulation patterns. There's a lot still to be known. But in any case, these are the numbers that we have, and about half, roughly speaking, about half the observed rate at the present time is contributed by these melting ice and snow reservoirs. So now for those of us who are worrying about adaptation, we again have to ask what the impacts of sea level rise could be. And the first thing to say is that global sea level rise is a wonderful thing to calculate, and it's something that a scientist loves, and it's one number. But in fact, if you live on the coastline, you only care about the sea level outside your dock, beyond your dock. And in addition, you could be in an area where the land is rising or subsiding due to geological or other processes. So that what really matters is the regional sea level rise plus subsidence. Okay? And as you can see from this map of reconstructed sea level trends, the sea level rise the rate has not been uniform worldwide. So in order to answer the question, when will the key impact occur, to me, we need to take these things into account. And a much greater precision in the forecasts will be needed.
Charlie, what are the stars on the slide?
Pardon me?
The stars.
Places where there are tide gauges, I think.
Oh, I see, okay.
So clearly the thing that everybody is aware of, and we all agree, is that the risk from storm surges increases if the sea level goes up. And of course the perfect storm is when the storm surges occur at seasonal high tides. And then you worry about beach erosion, your ocean-facing infrastructure, that's saltwater intrusions, wetland ecology. And I'd just like to point out that there's a new result for the Atlantic hurricanes that needs, of course, to be completely assessed, but it's interesting. It says that frequency of Katrina-like events will increase 2 to 7 times for each degree centigrade increase in temperature. And recall that we think we're going to get 2 to 2.5 degrees over today's 0.8 by mid-century. So who's the most famous group that is affected by sea level rise is the group that played the least in causing climate change, the low-lying island nations. If you look at them, here's the Maldives, a completely populated small islands, Kiribati, there are many others, and they are already considering wholesale moves to the mainland, hoping to find places, enclaves, where they can continue their national sovereignty while surrounded by other countries, much as Indian reservations are in the U.S. But well before these atolls are underwater, they're going to suffer saltwater intrusions, and it's going to destroy their crops. And so well before the moment when it's clear that they're underwater 100% of the time, their economic base for existence is going to be severely threatened. And the question is not to predict when they're going to be inundated, but when that will happen. Here's another area of great vulnerability. Here's a picture taken from space of the Nile Delta. You can see that almost all of Egypt's, just from the electric lights, almost all of Egypt's 80 million population lives along the Nile River or the Delta. The Delta is still some of the most fertile agricultural land in the world. It was also that way in times of the Roman Empire, and it was Nile agriculture that fed ancient Rome with grain to a very great extent. So here is a digital elevation map of the Nile Delta. It's shows, just look at the blue area, that's where a sea level rise of 1 meter would cause salt water intrusion independent of the storms. And that would have a serious impact on agriculture. All right? Now, keep in mind that if you look at that coastline, it's probably about 200 kilometers, just about 100 miles long. But think of the difficulty of protecting it and correcting it. I must say that the Egyptians are very aware of this problem. They've been managing the water of the Nile for about 4,000 years, and they very well know that they have a problem. Whether they can afford to fix it is a different question. Another area of great vulnerability is the Mekong Delta. Those are the blue areas, 1 meter sea level rise. And there's a research institute there that says that many of the provinces will be flooded in 2030. That may be an extreme case, but nonetheless it's quite clear that the most productive agricultural region in Vietnam is also very close to sea level and is also threatened by saltwater intrusion. Now let's look at the places. This isn't just a problem for the rest of the world. Let's look at the places in the U.S. where that are vulnerable to a 1 to 2 meter sea level rise, relative sea level rise. Remember, always relative. But there you see New York in 2 meters. Wall Street is underwater. South Florida is extremely vulnerable, as you know if you've been to the Everglades. We know about Louisiana from Katrina, and there are the vulnerable regions in the Northeast, and as we know from Superstorm Sandy, they are indeed vulnerable. So we're not going to get off scot-free. In fact, the OECD, the Organization for Economic and Cultural Development, have picked the 20 most vulnerable cities in the world to sea level rise. And it's not entirely clear what their criterion is. It's a mixture of the size of the vulnerable population and the value of the capital infrastructure in the area of vulnerability. But in any case, Miami comes out first. Guangzhou in China comes out second. Newark, Kolkata, Shanghai, Mumbai. So who would have thought that the United States has the first and the third most vulnerable regions to sea level rise in terms of threatened population and dollar value? How they decide between Mumbai with 11 million people and only 1.6 trillion in capital infrastructure, and Miami with a smaller population but a larger value of infrastructure. How they decide that is not entirely clear, but the essential point is that these big metropolitan areas are the ones that are going to have to cope with it. And it's not surprising that cities actually are amongst the most alert, city planners are amongst the most alert to the problems of sea level rise.